All right, good morning, evening, afternoon, everyone, depending upon exactly where you are. Oops. Sorry, I have to kill the echo there. So we're going to start a few minutes early here as a way for people to come in. If you're here early and you want to introduce yourself in the chat, feel free. If you want to ask any questions as we just kind of chill for a few minutes here, don't hesitate. Um, Might as well take advantage of the time. As you may tell, I'm a little sleepy. It's a bit early for me, and didn't get too much sleep last night, despite going to bed early. Um, we'll see how we go. I just need to lock into that kind of like automated talk giving mode, and we should be all good. Um, but yeah, otherwise we'll chill for 10 minutes or so. Give people a chance to come in. I'm going to keep looking down at my phone because my laptop's clock is all messed up at the moment. Um, and yeah. Of course, I always go back to the bizarre music from Earthbound if that's a more appeasing wait time for everyone. As we go through, if you have any questions, you're welcome to drop them here in the YouTube chat, or you can also drop them on the Patreon page. You need an account for both, unfortunately. You need a Patreon account to drop comments on the Patreon post. You don't need to be a paid subscriber or anything. You just need a Patreon account, so it's free. It requires some registration, a throwaway email, and the same with the YouTube chat. You need some kind of YouTube account to drop a comment. If for whatever reason you're watching either live or in the future, and you have a question, but for whatever reason weren't able to ask via the Patreon or the YouTube, or don't feel comfortable asking, you're welcome to throw me an email. Contact info is on my website, and I'll do my best to respond in a reasonably timely manner. Again, if you're watching in the future on the VOD, you're welcome to probably jump 5-7 minutes in the future. We'll just be chilling here as people kind of slowly accumulate in. So probably not much too exciting happening for the next few minutes. Okay. Let me try. Christian, is that any better? All right, we'll see how that goes. If the audio is low or there's too much background noise, let me know. I can try to adjust the audio settings, um, especially before we get going proper. Um, uh, for whatever reason, so my audio is capping out pretty hard on um, on the stream side. I don't know if maybe you just have to increase the volume on your end. There's no music or anything. There's no background sound, so it's just my voice. So you shouldn't have any problem just amping your volume up if that's possible. If I go any higher on my end, I start saturating the levels. I think the audio quality will start getting pretty bad. Okay, great. Yes, sometimes this is that weird thing with, like every streaming service, their kind of nominal volume outputs are all different. So they all get normalized, and then some of them will pop in really loud, and you have to lower the volume. Some of them will pop in really quiet, you have to up the volume. I don't think there's any consistency or standardization in that. So unfortunately, I think it might be a YouTube issue. But as far as I can tell on my end, yeah, it's about as high as I can go before I start getting audio artifacts. But thanks for letting me know. If anyone else is encountering, again, any audio issues or anything, don't hesitate to reach out in the chat, and I will try to get those addressed as quickly as possible. I was about to say that for whatever reason, this talk seems to be a bit cursed. When I gave it in person, it was just a disaster of a sequence of continued disasters, where the room we started off in ended up nothing was working there, and so we had to go to a new room, and this is an entirely new building, so people weren't really familiar with the setups. We had to move to another room, and then start trying to move people who were showing up in person to the new room. And the new room, we finally got the video screen to work, but then none of the internet options were working. Of course, this is Imperial, so it's not like you can just join a guest network. You have to have multiple certifications and everything. It's the worst. The UK uni Wi-Fi's are just notoriously bad for things like this. Anyways, in the end, we eventually ended up hotspotting off somebody's phone, which worked out fine for me later on during my trip. There's a few circumstances where I did have to end up hotspotting off my own phone, which was fine. But I think the connection in that room, this new building, it was relatively high up. I'm sure there's a lot of metal and Faraday cagey like circumstances going on, so the signal was really bad. And so technically we were kind of set up connected to Microsoft Teams, but for whatever reason the connection wasn't good enough, and we were just getting garbage being sent out. So it was very, very hard to discern anything. The slides were unreadable, and I think the audio wasn't great either. But at that point we'd been working on this for like 35 minutes. And we were getting into being late on the in-person side. So hopefully doing it here again, I can control everything, and that will avoid too many of those issues. For those who are first coming in, we're just kind of chilling for a few minutes. We'll probably start in 3-5 minutes or so. Feel free to introduce yourself in the chat. You're also welcome to ask questions anytime. You can ask them now. You can ask them as we go through. If you don't have a YouTube account and you have a Patreon account, you can also ask questions on the Patreon. Just comment on the post. It should be public, so you don't need to be a subscriber or anything. The only issue is you do need a Patreon account to post. So whether it's YouTube or Patreon, they're both free accounts, so there shouldn't be any issues in terms of payment, but you do need a thorough email or something. And if for whatever reason neither of those are useful for you, you're also welcome to ask questions after the fact via email. Tag me on socials, and I'll do my best to address that. And just to repeat, if there are any audio issues or weird technical issues, let me know, and we'll try to get them addressed as soon as possible. The audio looks pretty good on my end. If it's a little low on your end, it might just be that the kind of nominal YouTube output is low. You might need to crank your volume a little bit. I'm eternally debating how much wiggle we want to give people before getting started, but I'm realizing that the YouTube VODs are scrubbable in real time. So if anybody's joining a little bit late and you catch us as we've already started, they should be able to just rewind and catch up. So we might as well get started and not waste anyone's time who did show up on time. So with that said, let's get started. For those who don't know the full kind of circumstances here, this is a talk I gave last month while I was visiting London. It was meant to be a kind of dual in-person and remote talk. Unfortunately, the remote part was through Microsoft Teams, and that ended up being a technological disaster. As I was just saying a few minutes ago, we had to change rooms. The Wi-Fi and internet were not really cooperating, and we just had to kind of abandon things, unfortunately, for the people who showed up remotely. So the goal of today is just to give that talk again for anyone who wasn't able to catch it live, and hey, now we have an opportunity to broadcast a little bit more broadly as well. So this talk, once it goes up, the Patreon page is public, and anyone can watch it after the fact as well. So if you like the talk, feel free to recommend it to colleagues, collaborators, and the like. The topic of the talk is generative modeling, and I'm kind of being intentionally ambiguous here because this term generative modeling has become really popular in a few different fields, but for different reasons. And so I'm going to kind of embrace that ambiguity initially, and then I'll come in and try to clarify a little bit about the different notions of generative modeling, compare and contrast them, and really kind of narrow down to this notion of narratively generative modeling, which is my particular topic of interest these days, which is not so much an algorithmic notion as it is in a lot of the machine learning and AI that we're seeing today, but much more of an interpretational and model building tool. Okay, so first and foremost, I do want to emphasize that all of this discussion is going to be done in the context of Bayesian inference. And just to make sure we're all on the same page, Bayesian inference is a relatively straightforward process, at least mechanistically. We start with a Bayesian model, or what also referred to as a full Bayesian model. And this is composed of two important contributions. The first contribution is an observational model. Now, mathematically, this is a conditional probability distribution. It's a collection of probability distributions. But we can interpret it a few different ways. We can interpret it as a collection of stories of how the data could have been generated. We can also think about it a little more heuristically as just a set of mathematical patterns that could manifest in the data without really any interpretation to it. Either way, okay. Yep, I'm noticing, for whatever reason, there's a delay in... If I don't have that window up front. So let's see. Hold on, let me just adjust something here. Okay, so we'll go there. There. Okay. Let's double check if this is a little bit more prompt. Oh. Okay, that's a little bit better. Sorry, Keynote was acting a little bit weird. Again, curse talk for whatever reason. I never had any of these issues before. I can't explain it. Anyways, right. So a Bayesian model composed of two components. We have an observational model. Again, we can think of this as a collection of mathematical stories. We can also think about it as a collection of mathematical patterns. Either way, we get the same kind of mathematical form. To that, we're going to add a prior model. And a prior model is our opportunity to incorporate whatever domain expertise we might be available in a given analysis. Right? This is one of these common misconceptions with Bayesian inference that has real practical consequences, where people kind of overthink the prior model a bit. Right? They kind of believe that they have to incorporate all of their domain expertise, which is an incredibly overwhelming challenge. in practice, both to kind of reason about what you know and then translate that into an explicit mathematical form. That's not something we can do in a finite amount of time. Fortunately, you don't have to do that in any given Bayesian analysis. The prior model is, again, an opportunity. We can incorporate what domain expertise we might think is relevant, that happens to be readily available. It does not have to be our entire implicit knowledge about a system. Regardless of what information we're incorporating into the prior model, when we combine that prior model with our observational model, we get a joint probability distribution over both the observational variables and the model configuration variables. And this is what I refer to as the full Bayesian model. This joint probability distribution is nice for a few different reasons. From an interpretational perspective, it encompasses all of our assumptions, right? All of the assumptions that we make, regardless of whether in the observational model and the prior model, are now really in the same footing here. Sorry, getting YouTube errors. Okay, I think we're okay. Regardless of the kind of nature of the assumption, they're on the same footing here mathematically. And that I think it helps us kind of get around some of these really unproductive discussions about, what's a good assumption versus a bad assumption. Why are assumptions in the observational model okay, but assumptions in the prior model are not okay? When you get to more complicated models, is there a distinction between a prior model and an observational model? When you have a lot of latent structure, is that latent structure part of the prior, or is it part of the observational model? A lot of these kind of superficial discussions really aren't relevant if we only focus on this joint probability distribution. So it has that kind of nice unifying feature to it. The other nice benefit of the full Bayesian model is that once we've constructed it, Bayesian inference is pretty much mechanistic. We just turn a crank and everything happens automatically. In particular, if I take an explicit observation, which I'll denote with a tilde, and I plug it into the full Bayesian model, I immediately get, up to normalization, a posterior density function. You'll often hear that Bayesian inference is expensive, that constructing a posterior is this overwhelmingly computationally demanding task, and that's not true at all. It's extremely straightforward. You're partially evaluating a function. This happens automatically. What is difficult about Bayesian inference is not the construction of the posterior, it's extracting information from that posterior. Because even when we partially evaluate on the observed variables, there's going to, in general, be a lot of model configuration variables. Theta is going to be a big high-dimensional space. How do we reduce that posterior density function over this high-dimensional space to something that's sufficiently low-dimensional that we can perceive it in a correct way, in a faithful way? How can we visualize features of the posterior? And it turns out mathematically, the only well-posed way to extract information from a big high-dimensional probability distribution like this is with expectation values. So we take questions in the form of functions, and then the answers we get back are these expectation values. And so you can think of this in terms of means, other moments like variance and skewedness and kurtosis and things like that. You can think about quantiles, which are kind of empiric or inverse expectation values, if you will, but in practice they're computed through expectation values. Histograms are constructed from probabilities. Probabilities are can be written in the form of expectation values. Expected utility functions when you're doing Bayesian decision theory, right? These are all expectation values. Anything that's not an expectation value really isn't a well-defined probabilistic operation. So things like maximum a posteriori estimates, for example, they're really awkwardly behaved because they're not expectation values. So if we focus on expectation values, everything's going to be nice and self-consistent. Now, the only problem with expectation values is that they're in general going to be intractable to compute analytically. In a few simple cases where you have a very clean posterior and very nice functions, we may be able to derive these expectation values analytically. But in the most for most circumstances, we need to approximate them numerically. And that's where the real cost evasion inference comes in, right? It's the estimation of these expectation values. This is, when you run a tool like Stan, constructing your posterior happens almost instantaneously. That big, long time that you're waiting, that's the running of Markov chain Monte Carlo, which is collecting information to inform expectation value estimates. So the computational challenge here is estimating the expectation values, but from a conceptual perspective, it's still pretty turn crank, right? We can start with our joint model, our full Bayesian model. We plug in the observed data, we get our posterior density function, and then we use that posterior density function to inform these expectation value estimates. But all of that happens pretty much under the hood if we're using off-the-shelf tools like a Stan and the like. So if we're taking that computation for granted, the real challenge that's left is where that full Bayesian model comes from in the first place. Especially if we have a lot of data variables, if we have a lot of model configuration variables, parameters, if you will, we're going to be dealing with a big high-dimensional space here. How are we going to construct a joint probability distribution on this big high-dimensional space in practice? This is an incredibly overwhelming task. Really the only way we can make this more manageable is by breaking it down into smaller pieces. And that's exactly what conditional probability theory allows us to do. So conditional probability theory takes any partitioning of these variables and allows us to decompose the joint probability distribution into a sequence of conditional probability distributions. I want to emphasize here that there are many conditional decompositions that we can do to any particular joint distribution. Every partitioning of the variables, including the ordering, gives a distinct decomposition with different conditional distributions within them. Here I'm showing just one of these conditional decompositions where I happen to be decomposing it variable by variable, and I'm doing it in just the order that you see in the joint density function. So we start with y1, and then, it's not quite the order. We're going kind of yn to y1, and then theta I to theta 1. So we start with yn, which can depend on all of the variables, then yn minus 1 that can depend on everything except for yn, and so on and so on. And the key thing here is that all of these conditional distributions are one-dimensional. They have a lot of dependencies, but the actual probabilistic part of it is one-dimensional. And in practice, that's often much more easier to reason about. Now, anytime we're going to be talking about conditional decompositions, it can be very helpful to have a tool for visualizing the structure of those decompositions. What is the ordering of the variables that we're using? What is the grouping of the variables that we're using? What are the dependencies between these intermediate pieces? And this is where graphical models become especially useful, because they provide a way of very cleanly communicating a lot of this structure. So for example, let's say that I have 5 variables here, 2 data variables, 3 model configuration variables. I'm going to decompose them in this order, y1, y2, then theta 3, then theta 2, then theta 1. In order to translate this conditional decomposition into a graph, I'm going to take every one of these nodes and associate with them, every one of these variables, and associate with them a node. And then I can represent the conditional dependencies with arrows. So y1 can, in theory, depend on all of the other variables, and so there's an arrow from all of those other nodes into y1. y2 can only depend on the variables, can depend on every variable except for itself, and y1, which you've already peeled off. And so we get arrows from those nodes into y2, and so on, and so on. So we get these kind of dual pictures, right? We can think about the conditional decomposition as a sequence of conditional distributions and this final little kind of tailing marginal distribution for the last variable or set of variables. Or we can think about it graphically. There are complementary pictures to each other. To be completely formal, the graphical model is not a complete representation of the full Bayesian model, right? We know the dependencies. We don't know what those. We know what the dependencies are. We don't know the structure or form of those dependencies. And so we always need to kind of complete that with a more formal mathematical representation. But it's a great way of summarizing the overall structure. This is especially useful when there are simplifications in the dependencies, where some of the nodes don't depend on all of the variables they could, in theory, depend on. So, for example, I have the same model, the same conditional decomposition, but let's say in this case, the joint model has some simpler structure, so that y1 only depends on theta 2. It could, in theory, depend on y2, theta 3, and theta 1, but in this case, it just doesn't. Similarly, y2 could depend on theta 2, theta 1, and theta 3, but here it only depends on theta 3. And so on and so on, and we see we get a much simpler picture. And so this is especially useful. We're going to compare and contrast between different structural assumptions. This is the same space, the same observational space, the same model configuration space, but there are different joint distributions, each of which has these different consequences for the conditional structure for this particular ordering of the variables. So this is going to be a very handy tool to help us kind of understand what we're doing, to summarize the structure of the models that we're playing with, without having to get into the details of the particular conditional density functions everywhere that we would need to fill in if we're going to implement this in practice, right? But just when we're just kind of brainstorming and discussing some of the high-level structure, this is going to be more than sufficient. Okay, so we have these full Bayesian models that we want to build, or we want to work with in general. So we want to be able to build them, we want to be able to understand their structure, we want to be able to exploit that structure for computational purposes. But in general, remember, there's going to be many, many conditional decompositions. Every partitioning of the variables in the full observational space and model configuration space defines a different conditional decomposition. Some of these decompositions are going to be more useful than others, depending on the task at hand. So in order to define what a useful or a productive conditional decomposition is, we need to define some kind of criterion for what utility is. And this is where some of the nomenclature becomes kind of ambiguous, because there are different criteria that come up in different practical tasks in a given analysis. Each of those criteria will motivate different conditional decompositions, different conditional structure that's more or less useful. These different criteria, these different notions of useful, are often interpreted as generative, because they're following this kind of sequential structure through the model. So to get a better handle on what generative could mean and formalize it a little bit more carefully, let's think about some of these tasks that might come up in practice and how conditional decompositions play a role in facilitating those tasks. So the first task we're going to consider here is an algorithmic task. And I'm going to refer to this as procedurally generative modeling. Procedurally because it's all about constructing an explicit procedure for generating samples. So a procedurally generative model is defined through some kind of explicit exact sampling mechanism. We have some kind of box that we can press a button on, and it will spit out samples from the full Bayesian model. Now, there are multiple ways of trying to implement an algorithm like this. The most famous these days, especially when it comes to the term generative, is done through a push-forward mechanism. So formally, we introduce some auxiliary space, X. We have some probability distribution on that auxiliary space. And we push forward that latent probability distribution onto our joint observational model configuration space in order to generate implicitly a full Bayesian model. And so depending on the structure of that latent probability distribution, and depending on the structure of this function phi, we'll get different full Bayesian models. If this comes across as a little bit kind of too abstract for you, what happens a little bit more mechanistically is that you take this latent distribution, you generate exact samples from it, and then you just evaluate this complex function phi on those latent samples, and the output of that function gives you samples from the observational space and the model configuration space. Right? So this is how the quote-unquote generative AI methods work, right? You have some kind of complicated machine learning algorithm, say a neural network, some kind of structured network, depending upon the particular algorithm you're working with, and that's going to define some complicated function phi, and then you introduce typically some very simple latent distribution, and what you care about is not the latent distribution, not the function itself, but rather the combination of the two and the outputs that you get. And you implicitly define some model through those outputs. Right, so that's one notion of generativity. But it's all about this ability to generate samples. And that's it. Now, there's another way of generating samples that has much more to do with the conditional decompositions that we've been talking about. And this is referred to as ancestral sampling. If I can generate a sample from the first variable in this graph, and then I can generate a sample of the next variable conditioned on that first sample, and so on and so on. This sequence of conditional samples ends up giving me a joint sample from the full space, the product of the observational space and the model configuration space. And in theory, if I can decompose these variables down to one-dimensional variables, I can always just brute force this with projection sampling or something like that. And so the kind of key here is that if I can decompose the model into a fine enough set of variables, then I can potentially, I should in theory always have some kind of algorithm I can use to sample those conditional pieces and generate a joint sample sequentially. So from this perspective, a useful conditional decomposition is one that really makes that ancestral sampling as straightforward as possible. So for example, if there is a conditional decomposition such that all of the conditional pieces end up being well-known families of density functions, and that, for example, all have pseudorandom number generators associated with them, so you can grab those pseudorandom number generators from R or SciPy or NumPy or whatever tool you're working with, and run those, then ancestral sampling becomes extremely straightforward to implement in practice. That said, there might be multiple conditional decompositions that allow that kind of ancestral sampling. There might be multiple ancestral conditional decompositions, some of which are a little bit more straightforward than others, right? So there might be a spectrum of possibilities here. But the key feature to keep in mind is that we're focusing on this algorithmic task. How can I generate samples from the full Bayesian model? Is there a way of using conditional decomposition to facilitate that process? Any questions about this notion of procedurally generative modeling so far? Its relationship to conditional decompositions, to the full Bayesian model, and the like. So the key reason I introduced this notion of procedural generativity, is really just to try to remove this topic of generative AI entirely. Yes, the term generative AI is not the worst term in the world. There's a lot worse abuse of vocabulary and statistics in machine learning these days. It does connect to the kind of underlying algorithmic structure of these methods, but it's not the kind of generativity that I want to focus on here today. So now that we've kind of laid that out, we can move on to a second notion of generativity that I'll refer to as narrative generativity. Narratively generative modeling is not about any kind of algorithmic task. It's about the modeling task itself. It's about interpreting the full Bayesian model, the structure of a full Bayesian model, either to allow us to better understand the consequences of the assumptions that are built into an existing full Bayesian model, or, even more importantly, to build up a relevant full Bayesian model in the first place. And so the idea here is that it's, a conditional decomposition of a full Bayesian model is narratively generative when it has an interpretation that follows the structure of the data generating process. We're not just considering the final output of the data generating process, just the final data that gets dumped into our computer on a piece of paper, or however the data is being collected. But what are all of the steps in the generation of that data? What are all the things that happen along the way, from the things that we really want to understand to the final data and everything that happens in between? So from this perspective, a useful conditional decomposition is one that mimics that data generative structure, where each piece in the conditional decomposition tells a particular part, an aspect of that data generating story, right? So this is really an interpretational perspective. I can take a full Bayesian model and decompose it in large number of ways. They're all giving the same mathematical model, right? They're all just different representations of that same joint distribution. But one of those is going to be most aligned with our understanding of the true data generating process than any of the others. And that's the one that's going to be most useful for model building. Now, this might sound somewhat abstract, but it's something that we often do pretty implicitly. For example, let's say that I have a model where I have two data variables and two model configuration variables, right? Often, just implicitly, just by default, we'll talk about things like the data being generated from the parameters. Decomposing this space into the observational space, the model configuration space, with a clear directional dependence of the data variables on the model configuration variables, right? This is a conditional decomposition, and it's a narratively generative conditional decomposition because it follows the data generating story. The data has to come from somewhere. It has to come from some system that we're modeling with these two variables here. Now, we can take this a lot further. We can take this kind of default that we'll often do of separating the data as being generated from model configuration variables and decompose this further to tell a more refined story. In fact, there's lots of stories that are compatible with that initial decomposition, each of which corresponds to a different data generating process. For example, let's look at this one here on the top left. The two data variables are coupled together in a single node. The two model configuration variables, however, are separated. This conditional decomposition tells a story where we have these two latent phenomena modeled by theta 1 and theta 2. And the observations are informed by both of those latent phenomena. But importantly, those latent phenomena are not coupled to each other. They're not interacting with each other. Contrast that to this conditional decomposition, where now there's a dependence of theta 2 on theta 1. So the kind of final step of the data generating story is still the same. Y1, Y2 get generated at the same time and formed by both of these latent phenomena. But now the phenomenon modeled by theta 2 is interacting with or is influenced by the phenomenon modeled by theta 1. And we can also have these kinds of dependencies, these interactions, these influences happening on the observational side as well. In this data generating story, y1 gets generated first, and then the output of that first component observation influences the output of the second component observation. This is kind of an awkward data generating story if you think about it. How does the output of one observation influence other observations, right? There has to be some kind of feedback where that observation somehow changes the way that we study the system, which then influences further observations. And that awkwardness is a good sign that this would not be an appropriate data generating process for a lot of applications. That said, there are definitely going to be some where it is appropriate. Think of, for example, an economics model. Somebody reports GDP. Think of GDP as this kind of observation of the economy. Well, the economy then takes that reported GDP and changes its behavior depending upon that report, right? People are influenced by that initial observation. So then future reports, even if they only depend on the latent system and not that observation directly, are going to be at least indirectly influenced by the outcome of that first observation. So there's like a kind of empirical autocorrelative structure that gets built into the model. And this is the utility of this narrowly generative perspective. We can take each of these conditional decompositions and translate them to a mathematical story of how the data is generated, or how the data could be generated. And we can contrast those mathematical stories to our domain expertise and try to identify which of those stories are more or less appropriate in a given application. So if we want to move away from black box analyses and black box estimators and black box algorithms and build our own models informed by our understanding of a system, then we need to follow this data generating structure. And this narrowly generative perspective really gives us the tools to make that as productive a process as possible. Instead of trying to reason about how do I construct a big complex probability distribution, we can instead think about where did the data come from? What's the story here? And then we can build a model on top of that story. I do a lot of consultation in my consulting work. It's a little redundant. But a lot of my consulting engagements, whether it's with industry clients or academic clients, there's often initial hesitancy about making assumptions or building a model. And a lot of that comes down to the fact that people don't have experience doing that. They have a sense they want to build a Bayesian model, they want to invest the time to do this in a careful way, but they just don't have the tools to develop those models on their own. And if you focus on that step as just this kind of pure mathematical step, it's not very productive. People just start trying to throw together families of density functions that they may have seen before, right? There's this kind of common problem that you'll see where the question isn't, what's the structure of the model that I need, but rather, do I need this family of densities? Do I need this family of densities? Can I just slam these two families of densities together, right? It's almost like a toddler trying to cram together these different toys and not really understanding how they fit together. But I can take, in every one of those circumstances, if I reframe the problem, and instead of focusing on this mathematical problem, if I just ask them where the data came from, every single time I'll get these incredibly detailed, complex stories of the data generating process. These people are experts in this. They know the story. They're just not aware that that story is relevant to the model building process. So by starting with that story, we can really isolate the relevant domain expertise, lay down a foundation for our model, and then the pieces start fitting in a much, much more productive way. So Christian's commenting in the chat that this domain expertise is also needed for non-Bayesian models, hence why subjectivity is not really a Bayesian thing. Yeah, so Bayesian models often get kind of pinged for being subjective and hence somehow less good than other methods. But every probabilistic inferential method, whether you're Bayesian or frequentist or you claim that you'll use whatever method is useful in a given application, which means you just do a lot of bad methods and have no criteria for what's good or what's bad. You're making assumptions, and those assumptions are going to be subjective. There is no objective way to construct a correct model in any given application. Every method you use is based on assumptions. Those assumptions might take different forms. Sometimes they're very explicit assumptions. Sometimes they're very implicit assumptions. A lot of methods are built on things like asymptotics, which people kind of treat as these universal assumptions that always hold. And they don't in practice. So the kind of frustrating thing with the Bayesian frequentist divide in practice is that there's this unfortunate misunderstanding, or this false belief that Bayesian methods are more assumption dependent, hence more subjective, and frequentist methods are not. Firstly, all these methods depend on assumptions. What makes a method more or less useful is how transparent those assumptions are, and hence how well we can critique them and understand what assumptions are appropriate in a given application. And that's really where Bayes methods shine. Because we build these models, the assumptions become much more explicit, especially when we embrace this neurogenerative perspective. Contrast that to a lot of frequentist methods that rely on asymptotics that are extremely difficult to validate in practice. Right? It's very easy to just wave your hands and say asymptotics n greater than 20, which I hear so often. Once n is greater than 20, some kind of phase transition happens, and all of a sudden assumptions go away, and I don't have to worry about anything. Absolutely not how asymptotics work. You have to verify that asymptotics is the results you get from asymptotic analyses are good approximations to what you're actually seeing in practice. That's an extremely difficult task at hand, and most people don't have the training to do that. And so people end up using these methods without knowing if they're appropriate or not. And that's where we get so many of these fragile analyses. So assumptions are paramount to any kind of statistical inference or decision making. There is no objective-subjective divide, right? The only kind of separation you can possibly argue between subjective and objective is that some assumptions are good and some assumptions are bad, and that's more about convention than it is about any underlying scientific truth. Convention is not objectivity. What really matters is transparency versus opacity, and transparency is something that we get from this neurogenerative perspective. So beyond philosophical discussions, philosophical arguments, one of the reasons I really love this neurogenerative perspective is that it really allows us to formalize a lot of model building tools and motivate tools we may not have been aware of in the first place. A lot of the stuff that we'll be talking about today, people often do implicitly, but they might do in a more heuristic way than ideal. But if we really embrace this narratively generative perspective, this ability to connect a data-generating story to an explicit conditional decomposition, and then build up a model around that decomposition, this gives us a way of formalizing a lot of heuristics that are popular in practice to make sure that we use them as productively as possible. So I want to spend the rest of the lecture today just talking about some of these techniques and their relevance in practice. These are not going to cover all of the techniques that we can get out of this perspective. I'll talk about some references for follow-up at the end. But just some of the kind of key features or key techniques that come out of this perspective. So the first one I'll talk about here today is what I'll refer to as serialization. When you're telling a story, you can think of that story as this one big monolithic arc, but often it's more useful to break that arc down into smaller pieces, into smaller stories. Right? You can build an arc down into a series of novels. Those novels can be broken down into a series of chapters. Those chapters can be broken down into a series of scenes. when we're telling a story, it's often most helpful to think about it as each story as a collection of stories, and those individual stories as themselves collection of stories, and so on. And the same thing happens when we're telling a mathematical story. So we can think about our full Bayesian model as just one big monolithic entity, where we have this big high-dimensional variable, theta 1. And this comprises all of the relevant structure at the same time. But we can also zoom in to this big monolithic blob and resolve some of the substructure and think about it more as a collection of smaller models that are pieced together in an appropriate narratively generative structure. And then those pieces we could zoom in on and refine them into more detailed mathematical stories, and so on and so on. And what this allows us to do is approach model building from different directions depending upon what might be most useful at any given time. For example, if the overall data generating story is just a little bit too overwhelming, we don't have to start there. You can zoom in to the level of detail that you need and just start with one part of that data generating story. And then build out around that initial piece as is useful, as is convenient. So we might start with this little piece of the story and then expand it back. Tell the part of the story that hasn't yet occurred. And then we proceed telling the story forwards at this level of detail, just focusing on each step one at a time to make this modeling task less overwhelming. At the same time, sometimes these details are the thing that becomes overwhelming in a given analysis. In that case, maybe it's helpful to step back and think about that broader arc, starting with a relatively crude model that captures the overall structure. And then we can refine that model piece by piece as is convenient in the given analysis. Either way, we should get to the same model. The point here is that we have multiple paths of getting to that final model. And we are free to take the path that is most useful in any given application. If we're getting bogged down in the details, we can zoom out and think about the overarching arc and try to expand on that. If that arc is getting a little bit too overwhelming, we can zoom in and focus on one part of the structure. But so long as we're treating these pieces consistently with each other, we should end up at some final model that is appropriate, that is relevant for the task at hand. And again, this is the real kind of key here, is that we don't want it to try to automate model building. That's not going to be something that's going to be practice. We want to make model building as straightforward as possible. And sometimes that means having many ways of implementing a model, many ways of developing a model, recognizing those multiple paths, and then choosing the path that is most convenient for us in any given application. Now, another technique that comes up a lot in storytelling is what I refer to here as mixing genres. Right? The most rich, engaging stories out there are the ones that combine different styles together. Right? The ones that don't fall into stereotype, rather cross different genres and combine them in as useful way as practice. And the mathematical analogy to that I want to talk about here is combining different pieces together that have different levels of interpretability. And so just to demonstrate that, let's say I have these three pieces. The top piece, just with the data variables, let's say has a strong narrative generative interpretation. In this case, I know that the individual component observations are all generated independently of each other. And I've got this bottom piece that, say, is maybe motivated by a very rich phenomenological theory in a given application. The problem is that I can't connect that theory to the observations directly. There's some other piece, there's something that happens in between those two pieces. And for whatever reason, we don't understand that part of the story as well as the other parts of the story. And so we can come up with a more heuristic model for that, but it's not going to have the same richness of interpretation as the other parts. And the question is, are we dead in the water at this point? Does one non-narratively generative part of the model kind of corrupt the entire model? Is it the stereotypical bad apple? Well, it could be, but also doesn't have to be. Provided that this heuristic piece has this sufficiently flexible mathematical structure, and most importantly, provided that we incorporate it into the rest of the model in a narratively generative way, we can still build up a useful model. In other words, narrative generativity is not a binary qualification of a model. Models can be more or less narratively generative depending upon how interpretable the overall arc is, as well as these individual components. Ideally, our model will be as narratively generative as possible. We want to have as much interpretability and understanding in all of these pieces as we can. But we don't want to have that stop us from building a practical model in a given application. Right? If there's one piece that we just don't know that much about, then that's all we can do is model what we happen to know. And if that leads us to a heuristic model, that's the best we're going to be able to do, and that's okay. Now, this might sound a bit abstract, so let me anchor it in an explicit example that does come up quite a bit in a lot of applications. So let's say that I'm trying to build an analysis, and I want to isolate some signal, right? There's some kind of signal process that I really want to learn. But that signal process is contaminated by some irreducible background. I can't get rid of that background. How do I model this in practice? Well, if I have a rich theoretical understanding of that signal process, then I can use that theoretical understanding to build a narratively generative model for the signal. But the background is often more challenging. We might have a sense of what's contributing to that background, but it may not be a rich enough understanding to really model it at a detailed level. Certainly not the same level of detail as the signal. And so we might incorporate a more heuristic model here. Right? A model, just a mathematical model that has sufficient flexibility, a polynomial model, a spline model, just something that has the right kind of structure to capture some of the patterns we expect to see in background, but not in the signal. And by combining that with the signal model, we get an overall narratively generative model. And provided that background model is sufficiently flexible, we can isolate the signal and leverage that rich theoretical understanding to infer these, the details of that process. So we can manage that contamination in a productive way, even though we have a more heuristic model for that part. And this is where I think a lot of machine learning and AI methods can be made practical. Right? A neural network is not a probabilistic model. A Bayesian neural network is not a thing. Right? You need to take that neural network and you need to embed it in a probabilistic model. Say you have a regression model, and you take your baseline function and replace that with the output of a neural network. Great. Now it's a probabilistic model. But it's not just that neural network, it's the neural network and the structure around it. And so what makes for a useful model in that vein is that initial structure and where you incorporate that machine learning method. And at that point, it's really just another probabilistic model. It's not really anything all that special, right? We have a context. We can use that context to understand the kinds of behaviors we want from that machine learning component. And that can inform the right kind of regularization and prior modeling. And provided we can actually implement that kind of regularization, we can get a really productive model. And people, often treat this as a special thing. You'll have terms like physics-informed machine learning, which just hurts me at a deep, fundamental level. Because it's just a model, just like any other model. It just happens to have this one fancy piece in it. But that fancy piece doesn't make a useful model. It's the structure, the context around that fancy piece that allows us to use that fancy piece in a productive way. And that's this narratively generative perspective that really helps us understand that context. Another common feature that you'll see in really good stories is multiple narratives woven together. It's not just, one story of one individual. You'll hit multiple stories of multiple individuals happening at different times, happening at different locations, right? Everything kind of gets woven together into a complex narrative. We can do the same thing probabilistically. In particular, our models don't have to contain a single data generating process. If we have data that's coming from different sources, then we need to model those different sources. We need to model the different data generating processes that are giving rise to the data that we're observing. So we can always kind of try to lump that all together into a single monolithic data generating process, right? We can look at this graphical model here and think about this as just one single data generating process that's generating y1, 2, 3, 4, and 5 all at once. But from a narrowly generative perspective, it's also often helpful to step back and think of this as a collection of different data generating processes that have been combined together in a consistent way. So, for example, we might think of this as one data generating process responsible for generating y1, 2, and 3, and then a separate data generating process responsible for generating y4 and y5. By reasoning about these different data generating processes and how they're coupled together, we can inform a joint model of the two, which allows us to turn that Bayesian crank and get consistent inferences and predictions out, no matter how complicated or idiosyncratic these different sources of data might be. Right? Data fusion is really just a modeling problem. And once we've built that model, there's nothing left to solve. The inferences and predictions are derived just as they are with any other model. So, for example, let's say that I have data from this first data generating process. I have observations for y1, y2, and y3. But I want to make predictions for y4 and y5, right? I don't care about making predictions for things I've already observed. I want to make predictions for this new circumstance that I haven't quite seen yet. Now, my inferences, my observations y1, y2, y3, they don't directly inform y4 and y5, but they do directly inform it through the joint structure of this model, right? In particular, inferences for theta 1 through theta 6, that's going to inform theta 10, theta 11, which then informs y4 and y5. But and this can be, if you think of this as two different steps, this can be a really complicated process. How do I take, construct inferences from y1 through y3, and then propagate those inferences into a separate prediction step for y4 and y5? Well, from a Bayesian perspective, I don't have to do that. I just build the joint model and I turn the crank. When I plug in the observed data, I get a joint posterior, not just for all the parameters here, but also for the unobserved data variables y4 and y5. And then if I marginalize out all the parameters, what's left is a predictive distribution for y4, y5, given the observed y1, y2, and y3. And the mechanics of constructing that predictive distribution are the same as constructing any other predictive distribution in a Bayesian analysis. The only thing that's different is that joint model. And this discussion of multiple data generating processes leads us into a tricky topic of causal inference, which I'm going to absolutely scare quote the hell out of here. I come from a physics background. And so when I hear terms like causality, I think of a physical system. I'm thinking about events in space and time that influence each other in a very particular way. And the sequence of causal events then informs the kinds of behaviors you might see in a given system. Now, if you have this kind of causal understanding, this physical causal understanding, you can absolutely use it to inform an appropriate narratively generative model. And so from a pure, philosophical perspective, if you have this very formal causal understanding of a system, absolutely use it to inform the kind of models that you want to build. I would argue that's absolutely within the scope of this narratively generative perspective. However, a lot of methods that are tagged as causal inference these days, I would argue, don't really have much to do with causality. At least not in this formal sense. And people will disagree and argue about what they mean by causality, but my best attempt of trying to kind of summarize all these different notions of causality is that it has less to do with why things are behaving the way they are, but rather understanding what behaviors are changing. So I think it's fair to say, and again, this is an opinion, not something that I think is going to be necessarily universally agreed to, that most of the time when people refer to something as causal, what they're really referring to is some kind of inference or prediction under a changing data generating process. And one of the reasons why a lot of causal inference might appear to be familiar, or not necessarily trivial, but kind of redundant to things that you may have seen in the past, is because they kind of are, right? This problem of tackling inference and predictions in a changing world is not something that is new. That is not something that's recent, right? Things like interpolation, extrapolation are an example of that. In-sample versus out-of-sample. Transfer learning, model drift, concept drift, right? These are all vocabulary that's been developed over the past few decades, if not longer, to try to describe this problem of how do we learn about data in one setting and translate those inferences into another setting. Now, from a narrative generative perspective, there's really nothing special about this problem. We tackle it the way we tackle any other modeling problem. We just model the data generating processes at play. If we're talking about a static data generating process that doesn't change between our observations and our predictions, then we just model that one data generating process. And we should have separate pieces at the end for the observed variables and the variables that we want to predict. And that gives us this joint model. And as we've already seen so far, once we have that joint model, there's nothing left to do but turn the crank. There's no causal Bayesian inference algorithm. Everything is in that model. So for example here, if I want to make a prediction for y pred given y obs, what do? Well, I take this joint model, I partially evaluate it on the observed variable, on the observed data. That gives me a joint posterior for the parameters and this y pred variable. At this point, if I want to isolate the predictive structure, I just marginalize out the parameters, the model configuration variables, and that gives me a predictive distribution for y pred given y obs. Right? Everything is completely mechanistic once we have the joint model. And the magical thing is it's the exact same process if the data generating process is changing. We just have one data generating process for describing how the observed data behaves. And then we have a second data generating process to describe how predictions might behave. We have to model what's changing. Once we've built that joint model that incorporates both of those data generating processes, we're effectively done. Everything's mechanical at this point. We partially evaluate the observed data, we marginalize out the model configuration variables, and we get this predictive distribution. And you could argue this predictive distribution is now causal, but it's really no more causal or less causal than the model that came before. It's just based on different assumptions. But there's no challenge in building a model on the assumptions of a static data generating process or a dynamic data generating process. It's all the same approach. And it doesn't matter why the data generating process is changing. whether it's something that's beyond our control or something that we're actively doing to the system. And so, for example, if you want to model an intervention, you don't have to think about a do operator or try to construct some kind of thing that updates your inferences or your estimators based on that change. You just model what happened before the intervention, you model what happened after the intervention, you put them together into a joint model, and you turn the crank. So I don't want to say that causal inference is trivial. I think it's more productive to say that causal inference is really just a special case of probabilistic modeling. And if you're embracing this neurogenerative perspective, it's going to come naturally. It's going to happen automatically as you reason about the relevant data generating processes. And so you can take this neurogenerative perspective and use it to better understand the assumptions that an advertised causal method might be making, and then judge whether or not those assumptions are relevant in your application or not. Or, my favorite approach is to just embrace the perspective from the beginning and use it to develop a bespoke model appropriate to the given application, and then use that for your analysis directly. So someone's asking in the chat, would the composition of sample population, for example, demographic variables, be an example for something that could change between the observed and predicted values? Yeah, absolutely. All right, so one example where neurogenerative perspective becomes really helpful is when you think about regression models, right? Regression modeling is not necessarily a neurogenerative model. It's just this mathematical model for learning the kind of conditional patterns of one set of variables given another set of variables. And the quote-unquote causal assumption that gets made when you use a regression model is that conditional pattern of y given x is static. It's the same for all of the data sets of interest. So you can take that conditional pattern and convolve it with any distribution of x's to get different distributions of y's. But if that conditional behavior changes, in particular, if the conditional behavior is coupled with the marginal behavior of the covariates directly, then you can't separate them out. You've got to build a joint model of the two, and only when using that joint model you get consistent inferences. So one of the kind of aspects of generative modeling that becomes really important is to think about all of the variables, right? You're modeling the entire observational space, everything you observe, not just some of the variables, all of the variables. And in a regression setting, that would mean not just the kind of outcome variable, but also the quote-unquote exposures, the demographics, things like that. When you build up a model of that behavior, following your understanding of the system, you might end up with something that looks like outcome variable given exposures / demographics, and then a model for the exposures and demographics that are uncoupled to each other. And so if you only care about making predictions for new outcomes given new exposures and demographics, then you don't need to worry about what that marginal exposure demographic model is, right? But that just falls out of the math naturally. If you build that joint model and run that Bayesian crank, you get the right answer out in the end. Worst case, you've done a little bit of extra modeling you might not have needed to do before. But in the process of doing that extra modeling, you have now verified the kind of decoupling of those two terms is actually appropriate for your analysis. So this is something I get into in my kind of intro regression chapter. It's under variate covariate modeling on my website, which I'll link to in just a second, where I take this regression model and think about it from this neurogenerative perspective, and kind of show what can go wrong when y given x and x is not actually following the data generating story, and the kind of complications that can arise therein. Another example that came up recently on the Patreon is an example where somebody had these kind of different measurements of a system, and for some of the measurements they had the true state of the system, which was a binary, basically like yes, no. And they were thinking about modeling this as a logistic regression. The problem that came in is that some of those measurements were missing, right? There's kind of missing this pattern there. So if you're going to do a logistic regression perspective, not only do you have to worry about all of the regression assumptions, but you also deal with the missingness. But the model became so much easier if you just thought about it from the narrow generative perspective, where you're not deriving the behavior of the system based on these measurements. You're deriving the measurements from the state of the system. And if you think about it that way, not only does the kind of model of the observed measurements become more straightforward, but the model of the missing measurements also becomes pretty straightforward. So just changing that perspective around makes it a lot easier to model all of those variables. And then if any of those variables are changing, you just take that change into account, right? Within the structure of your initial model, branch it off wherever things start to deviate, and then leverage that joint model for making consistent inferences and predictions, both for the initial data set and then whatever kind of hypothetical situations that you want to consider going forwards. Christian's asking in the chat, what are some red flags that your causal structure may not be correct? So this one gets a little bit tricky. One of the narrative techniques that I introduce in my when I have more time to go through this material is what I refer to as unreliable narrators. Right? Just because you write down a story doesn't mean it's right. Doesn't mean it's useful. And so we're still responsible for critiquing our models. So you can build a model that has two different data generating processes, one for, say before an intervention, one for after an intervention. It doesn't mean it's that model is actually a good approximation to the true data generating processes. Right? That's a model. We have to validate that model. That validation is relatively straightforward when we have observed data, right? So we can do these retrodictive analyses to see how well our model is able to reproduce the data that we've already observed. But when you're trying to make these predictions for new circumstances that you have not yet observed, you don't have anything to validate against. So all you can do is validate the parts of the model that influence the things that you have seen. And this is one of the challenges of thinking about counterfactuals and hypotheticals, right? The predictions you get, depending upon the structure of the assumptions in that counterfactual, in that hypothetical, which may or may not be relevant to any real system. So just like with the assumptions in your model, or just like any kind of assumption, you want to make those assumptions transparent so that you can at least critique them against your domain expertise. And that's another benefit of trying to incorporate those counterfactual / hypothetical assumptions into a consistent joint model. Because now everything is together. Everything is presented as one common entity. And they can all be critiqued together. Some of those assumptions can be critiqued with retrodictive checks. All of those assumptions can be critiqued against domain expertise. Whether it's your domain expertise or the people that are consuming your analysis. Right? Maybe they identify that the assumptions that you're making in your counterfactuals are not relevant to what they care about. In which case, they know they're not relevant, and they don't assume that those predictions are going to be relevant to them, which is exactly what you want, right? That's all you can ask for. So I think it's hard to say whether or not they're like distinct red flags, because so much of that validation of these counterfactuals, hypotheticals, etc., is only going to be based on domain expertise. And because of that, there's no, kind of mathematical process that we can really kind of distill that down to. We should be as transparent as possible. And then what will be a red flag will depend upon what we happen to know about a system and how much detail we have about that system, right? So I don't know. I think, just like with any other assumption, there's going to be layers to it. You might think at a very high level, is the system static or not, right? You could argue that's a causal red flag. if you're taking some kind of a model that's assuming a static data generating process, and you immediately go, oh, actually, but the data generating process isn't static, it's changing. That's a flag that you might consider. But I don't know if that's really kind of like a flag so much as just something that happens naturally when you contrast your model to your domain expertise from this narrative generative perspective. All right, so just before I open up to any last questions people might have, I'm happy to stay a little bit longer as well if people want to kind of just chill and ask questions about the material. I do have some links and stuff I want to present. So firstly, if you're interested in any of this material and you want to dig into it more deeply, I have a lot more that you can follow up on. If you go to my website, I have a ton of writing. Some of it is directly connected to the idea of generative modeling. So there's a chapter on this material. It's not quite as up to date as what we've seen here. So, for example, like there's not really discussion of causal inference as much. I mean, there is, but it's not very good. But it is much more comprehensive. So there's a lot more narrative generative modeling techniques in there, and there's a bunch of examples that might help kind of clarify and demonstrate why this perspective is so useful. And then there are also separate case study chapters, each of which takes a particular analysis and really kind of demonstrates its implementation from this narrative generative perspective. Some of these are using real data. Some of them are using simulated data for various reasons, but they're all kind of treating it from the same perspective. There's an understanding of a data generating process. How can we model the data generating process? How can we critique that model? How do we iteratively develop a model till we get to the kind of complexity that we need to inform the inferences and predictions that we care about? And then I also gave a kind of longer form version of this material last year. And that's available. If you go to my website, go to the speaking tab, there's a link to the YouTube video there. And that has, I'm trying to remember how long it was. It was like an hour and a half or a 2-hour lecture. So kind of an expanded version of the talk today. And then there was a second part where I went through an explicit example. So there was a kind of a business marketing example. And I actually went through with a code demonstration, kind of showing how I would build up the model using the graphical models and comparing them to the full kind of mathematical specification, and then a probabilistic programming specification as well. And then that example that I showed there is one of the case studies that I mentioned previously as well. So you can just look at the case study directly, or you can also go to the this review here and listen to me review it piece by piece. And then beyond these immediate resources, if you're kind of excited about this approach and this perspective and are interested in how it might apply to kind of popular modeling techniques, I am doing some courses in a few months. So in August and September, I'll be doing a series of 4 remote courses. Everything's online, covering particular Bayesian modeling techniques. Each consists of a lecture and then a pretty comprehensive exercise review in Stan, both PyStan and RStan. And it very much embraces this narrative generative perspective. So if you want to kind of see how to implement a Bayesian mixture model and then interpret it from a narrative generative perspective, how when do mixture models kind of follow a data generating structure, and when are they just kind of a more heuristic mathematical model, and when can both of those be useful in practice? That'll definitely be discussed in that first lecture, and then so on for the other techniques. I do nominally assume familiarity with Bayesian inference and Stan for these courses, so they're a little bit more advanced. That said, the exercises are extremely comprehensive, and if you've never used Stan before, you can almost learn Stan a little bit through those exercises. So if you're familiar with these techniques and want to use them as a way of kind of learning about probabilistic programming and Bayesian inference, also can be very useful. So take a look at those. The link is on my website, and I'd highly appreciate it if you sharing with anyone who might be interested. And if you want to follow up with new work that comes out following, again, these ideas and really kind of embracing this neurogenerative perspective, I've got contact info on my website. You can follow my socials. I've got a mailing list that updates once a month with new work I've put out. So pretty lightweight if you just want to kind of keep up with new things that are coming out. I also have a Patreon where you'll get access to, depending upon the level of support, you get early access to things. You might also get kind of bonus content and the like. A lot, I mentioned previously, a bunch of kind of neurogenerative examples come up in that kind of discussion within the community there. So a really lovely place. Speaking of community, I also have a Discord server, which is available in a few different places to get the link. But that's totally public and open, and that's entirely dedicated to just this neurogenerative perspective about model building and the like. And it's stand agnostic, although there is a lot of stand discussion there. But if you want to kind of follow up and have these discussions, if you don't have anyone to talk about it with and you want to kind of join a community, that's absolutely there and welcoming for anyone who'd be interested in these ideas. With all that said, I know we're a little bit late, so thanks for sticking with me here. Any questions about any of the material I've discussed today, or how it might apply to different circumstances that might be of interest for you? Only awkward thing with streaming, there's a little bit of a lag, so we have to just kind of patiently wait for people to have a chance to ask any questions they might want to ask. And I should also check to make sure anybody commented on the Patreon. I think we're good there. Thanks, Christian. Yeah, I think I'm getting a little bit better at kind of distilling this down to the key points. It's one of these things where, in hindsight, it either comes across as like a really substantial change of paradigm, or something that's pretty trivial. I think both can be true. As with a lot of really important ideas. But it's just one of those things where the more we kind of directly acknowledge and recognize that this perspective is important, the less likely we are to kind of veer off of it and just kind of maintain this productivity from embracing our understanding of the systems at hand. All right, so it doesn't look like there's any other questions. If other questions do come up, I would recommend dropping them in the Patreon. If you have a Patreon account, again, you don't need to be a subscriber. You just need to have a free Patreon account in order to drop comments. And then I would say beyond that, either email or finding me on socials and tagging me and asking a question. I will try to check the YouTube comments. The notification system can sometimes be a little bit wonky. So you're welcome to also ask questions on the YouTube comments, just with the caveat that there's a chance I might not see it, so you may want to tag me somewhere else just to remind me if you don't get an answer relatively in a reasonable amount of time. So with that said, thanks so much for everyone who's joining live. Thanks for everyone who's watching in the future. I hope the material was interesting to you. I hope it motivates some productive modeling in the future. If it does end up being productive and you know helps motivate a really cool analysis, don't hesitate to share. I always like hearing about these kind of neurodegenerative models and where they're successful, and even where you might have struggles, because that can help inform how to kind of improve the presentation of the material and refine some of these techniques to make them a little bit more useful in practice. So thanks again. Don't hesitate to reach out with any feedback, and I'll see you next time. Cheers.